Welcome back, everyone. If you're the kind of person who absolutely loves seeing how the deepest abstract algebra can actually untangle our physical reality, well, you're in the exact right place. Today, we're diving into a real mathematical masterclass in this explainer. We're going to look at exactly how the Adelic Langlands program, which is literally one of the most massive and unifying frameworks in all of modern math, provides this totally rigorous pathway to proving the notorious Kakeya conjecture. And we're going to get our hands dirty, looking right at the math and equations from the source material to see exactly how this works.
So here's our quick roadmap for today. We'll kick things off with the classic Kakeya geometry problem. Map out our unified Adelic pathway, translate that physical geometry into algebra, build a bridge using the trace formula, and then finally we'll disprove the whole concept of fractional spacetime. Let's get to it.
Our objective here is honestly pretty fascinating. We're taking what is a deeply frustrating physical problem, all about microscopic overlapping lines, and we're transforming it into this incredibly elegant, rigid problem of spectral analysis over the continuous ring of Adels. It's a massive leap straight from classical physical space into pure number theory. So let's just dive right in.
Section 1. The Kakeya geometry problem. Let's start by defining the core geometry we're dealing with.
It all begins with something you might be familiar with, a Besicovitch set. To put it simply, this is a fractal configuration in classical real space, Rn, that contains a unit line segment pointing in absolutely every possible direction. Now, the Kakeya conjecture makes a really bold claim about this. It asserts that any such set must mathematically possess a Hausdorff and Minkowski dimension exactly equal to n, meaning it simply cannot collapse into a lower fractional dimension no matter how tightly you try to pack those lines.
Now, classical harmonic analysis attempts to tackle this using the classical Kakeya maximal operator. Let's really break down this equation here. It takes a locally integrable function, f, and averages it over a microscopic, highly anisotropic tube. Notice the supremum there, taken over all translation vectors a in Rn, and that integral over the tube of width delta. The main issue? Classical math struggles incredibly hard to bound the extreme overlaps of these tubes as that delta parameter shrinks down to 0. The overlaps just get way too chaotic.
Moving on to Section 2, the unified Adelic pathway. Here's how we're going to lift this problem totally out of those messy classical constraints. This pathway gives us a truly brilliant escape route. Instead of fighting those geometric overlaps in real space, we start by lifting the line configuration straight into the affine Grassmannian over the Adels, which creates a smooth global indicator function. From there, we use the Selberg Trace Formula to decompose this into automorphic representations, and finally we evaluate the bounds using L functions to find a strict contradiction if the dimension is less than n. It's like a giant puzzle perfectly falling into place.
To really put this into perspective, we're contrasting the classical approach, trying to measure physically dense fractal overlaps in Rn, with this new Adelic approach. The Adelic method takes those exact same lines and maps them into an algebraic group acting on the continuous Adeli ring. We are essentially taking physical, spatial directions and turning them into pure arithmetic operators. How cool is that?
Which brings us to Section 3, translating geometry to algebra. Let's lay out a precise translation dictionary for this.
This right here is where the absolute mathematical magic happens. It's a direct translation from physical geometry straight into p-adic algebra. A physical direction vector in classical space literally becomes a projective line in p-adic space. And remember that really messy Kakeya tube averaging operator we looked at a minute ago? Well, it maps perfectly to a discrete double coset operator. The absolutely crucial point here is how we track the limits. The physical shrinking of our classical tube, where that scale parameter delta goes to 0, is completely replaced algebraically. It actually becomes a shrinking p-adic resolution parameter, the uniformizer power approaching 0. And the physical averaging over space? That's cleanly replaced by integration over a disjoint union of left cosets. It's a one-to-one translation.
Let's look a little closer at the algebra making this all possible. In the p-adic tube subgroup matrix, notice how those transverse directional components are multiplied by the uniformizer power. They are highly compressed, which exactly mirrors the extremely narrow width of our classical Kakeya tube. And to isolate this tube at a specific resolution, we use that diagonal eccentricity matrix. So when we run the Hecke convolution operator, we're literally summing over distinct p-adic line orientations. It is an absolutely perfect arithmetic match for spatial averaging.
All right, Section 4, the trace formula bridge. It is time to unite these two worlds.
Behold the Selberg Trace Formula. This mastery equation demands an absolute unyielding balance. Over on the left side, we've got the geometry, the sums of orbital integrals calculating the raw physical volumes of those intersecting tubes. On the right, we have the spectral side, the trace over irreducible automorphic representations. If those lines overlap densely on the left, that mathematical mass absolutely has to be perfectly absorbed by the eigenvalues on the right. No exceptions.
Let's explicitly contrast this so it's super clear. The trace formula forces a direct dialogue between these two domains. The Kakeya tube intersection volumes, which is that raw physical density of our Kakeya set, are fundamentally linked to the discrete Hecke eigenvalues and continuous phase localizations on the other side. They're literally two sides of the exact same coin.
Section 5. Disproving fractional spacetime. Let's go ahead and set a mathematical trap. To actually prove the Kakeya conjecture, we're going to assume the exact opposite is true, just to see if it breaks the math. What if a Besicovitch set could exist with a fractal dimension strictly less than n? Well, if that were true, the tubes would overlap so incredibly densely that they'd generate an uncompensated, highly concentrated mass of intersections. And because of the absolute balance of our trace formula bridge, this localized physical density acts as a massive spectral threat. It forces an illicit, completely broken mathematical divergence on the right side of the equation.
And here is exactly why that divergence is strictly illegal in the math. If the dimension drops below n, it forces the automorphic L function to develop a multidimensional pole, a singularity, just to the right of the critical line. But generalized Ramanujan bounds dictate that for any valid representation, the L function must remain perfectly holomorphic. That means it has to be completely pole-free and smoothly continuous in that region. The spectrum fundamentally shatters if it tries to absorb this geometric singularity.
The real genius of this proof is how eigenvalue growth is rigidly capped algebraically by the Satake isomorphism. Within this polynomial equation, focus right on that exponent k on the elementary symmetric polynomial. Because the unitary Satake parameters have to lie on the complex unit circle, the maximum evaluation of that polynomial is strictly locked to the integer dimension factor. The eigenvalues simply cannot scale at some loose, fractional rate to match a lower dimension. The algebraic polynomial literally physically caps the growth.
And this rigidity extends to the geometry of the Hitchin fibration too. If a Kakeya set could somehow shrink into a lower dimension, the vanishing cycles of the degenerating prim fiber would have to show this weird non-integer fractional scaling. But the global purity of intersection cohomology dictates a very strict rule. Monodromy actions are restricted to roots of unity, integer weight eigenvalues only. Fractional scaling is just completely algebraically forbidden.
So, let's build to our definitive extraction of the dimension. Starting with the asymptotic volume limit of our double coset, it scales proportionally to q to the power of k times n minus 1. By isolating that exponent through spectral projection, we get exactly n minus 1. Add back our invariant longitudinal axis, and boom, we get exactly n. Double coset volumes are built directly from the discrete roots of the Lie algebra. They cannot scale fractionally without literally shattering the entire mathematical foundation of the group.
So to sum it all up, we've successfully trapped the flaw across multiple different analytical domains. Whether we're looking at holomorphy constraints on L functions, Satake polynomial exponents, Hitchin fibrations, or the roots of the Lie algebra, the underlying arithmetic strictly prevents spacetime geometry from collapsing into a lower dimensional fractional packing. The math forces the dimension to be exactly n. The Kakeya conjecture is unequivocally true.
It is just incredible to think that the behavior of prime numbers in p-adic space fundamentally locks in the actual dimensions of the geometry we physically inhabit. So I'm going to leave you with this final provocative thought. Does the rigid algebraic quantization of these Adelic fields reveal that our everyday physical experience of spacetime is, at its core, really just an emergent, integer-bound holographic shadow of a much deeper number-theoretic reality? Thanks for joining me on this mathematical deep dive today. Keep questioning and keep learning.